Okay, so I now want to start talking about non-homogeneous equations. And I'm going to give as an example, I'm going to start with a diffusion equation. Now, when we're dealing in this context, there are basically two ways that a problem can fail to be homogeneous. That is a problem. That is two ways a problem can be non-homogeneous. And that is if there's an external term like a plus q of xt or something, which we'll deal with later, or if we have non-homogeneous boundary conditions. So that is going to be something like u of 0t is equal to a, and u of 1t is equal to b. And then of course we have our usual initial condition u of x 0 is equal to f of x. So far, all of our terms, all of our problems, both of these have been 0. And for the method to work, you really have to have that. Because, for example, if we try an eigenfunction expansion, we're going to get 0 is equal to the sum k equals 1 to infinity ck of t phi k of 0. Sorry, this isn't 0. This is a. Now, if phi k of 0 is 0 and a is equal to 0, this is okay. But what's going to happen here, if this is not 0 and phi k of 0 is not 0, well, if phi k of 0 is 0, this is definitely not going to work. If phi k of 0 is not 0 and we have this condition, well, the right-hand side is a function of t, and so we would think that as t changes, this is also going to change, which would mean it cannot be equal to a constant. Now, I mean, that's not necessarily true, but that's one of the reasons that we would expect to not be able to solve, or why we can't use eigenfunction expansions to really solve these equations with non-homogeneous boundary terms. So here's what we're going to do. We're going to introduce a function. It's going to be the equilibrium solution. So what is that? So ue of x is going to satisfy these boundary conditions. It's going to satisfy this PDE, but it's also going to satisfy its t derivative is going to be equal to 0. So its t derivative is going to be equal to 0. It satisfies this PDE and the boundary conditions. It will not satisfy, typically, it will not satisfy the initial condition. So if we plug it in up here, we're going to get ue double prime. Well, ue double prime is equal to the t derivative, which the additional assumption here is that that's equal to 0. So ue double prime is 0. So this means ue is going to be equal to c1x plus c2. Because if a function's second derivative is equal to 0, it has this form. And now the boundary conditions say that a is equal to ue of 0, which is just equal to c2. Okay, so this is equal to c2. And then we know that b is equal to ue of 1. And when you plug in 1 up here, you get c1 plus a. So therefore, c1 is equal to b minus a. So this is b minus a. Okay, so this is what we have. So this is the equilibrium temperature. So now what we're going to do is we're going to define a new function. So I'm going to record this information over here. ue of x is equal to b minus a x plus a. We're going to define a new function v of xt, and v is going to be u of xt, where u of xt is just the solution to this problem, the one that we really care about, minus ue of x. Okay, well, what problem does v satisfy? Well, I will let you guys show that the t derivative of v is equal to the double x derivative of v. Okay, actually, I'm going to do this. The t derivative of v is equal to the t derivative of u minus the t derivative of ue. Now the t derivative of u, it satisfies this, so this is equal to the x derivative of u. The t derivative of ue, well, ue satisfies this equation, so this is also the x derivative of ue. You know, they're both equal to 0. So the double x derivative of ue is equal to 0, the t derivative of ue is equal to 0. Now, by the linearity of the differentiation operator, this is just u, the double x derivative of u minus ue, which is equal to v. Okay, so what this tells us is that the t derivative of v is equal to the double x derivative of v. Not only that, if you look at v of 0t, this is equal to u of 0t minus ue of 0. Now, u of 0t, if u satisfies this problem, that's equal to a, ue is equal to a, and so they're both equal to 0. So in other words, v of 0t equals v of 1t, and they're both equal to 0. And the initial condition is going to be v of x0. V of x0 is going to equal to f of x, whatever this is, minus ue of x, which in this case is b minus ax plus a. Okay, so if we apply this, let's look at a specific situation. Let's look at the case where a is equal to 1 and b is equal to 2 and f of x is equal to x. Sorry, the last part here, I missed like the important part because I'm getting a little ahead of myself, and this is not the first time I've said this today, so I get a little confused over where I am. So this is a, b, this is f of x. Okay, so what's the point of doing all of this? Well, we know that v of x t, oh, sorry. Where is this? We know that v of x t is equal to u minus ue. Now we know what ue is. We have the formula up here for it. The equation that v satisfies is now a homogeneous equation, so we know how to solve that. In principle, we know how to solve for v. And so u is just going to be equal to v plus ue. Okay, so I don't know what was on the board immediately before this, but I made another mistake in terms of where I had things written. So u of 0t, I want to look at a specific condition. So before I had an a and a b and an f of x, I want to look when a is equal to 1 and b is equal to 2 and f of x is equal to x. Okay, so now ue of x, that is the equilibrium distribution, is x plus 1. If you plug in x is equal to 0, you get 1. If you plug x is equal to 1, you get 2. So this satisfies the boundary conditions, and of course it satisfies this equation as well, since the t derivative is 0 and the double x derivative is also equal to 0. So now we're going to define a function v. V is equal to u minus ue, where u is the solution to this equation. So as we saw, the t derivative of v is the double x derivative of v. V satisfies these homogeneous boundary conditions, and v of x0 is just going to be x minus x plus 1. So this is just going to be minus 1. So, okay, so now v satisfies this diffusion equation with homogeneous boundary conditions. And, you know, from the very first example I think that we saw doing separation of variables, this is k equals 1 to infinity. The only difference here is we have infinity instead of in. Bk e to the minus k pi squared t sine of k pi x, where the bk's are given by the formula bk equals 2 times the integral from 0 to 1. We're going to integrate our initial condition, which is 1, and then sine of k pi x dx. Okay, well, the antiderivative of sine is minus cosine, so that's going to cancel that minus sign. So this is going to be 2, and we divide by k pi. And then it's going to be cosine of k pi times 1. So it's going to be cosine of k pi, and then minus cosine of k pi 0. That's just cosine of 0, which is equal to 1. Now, when k is odd, cosine of k pi, like if k is 1, cosine of k pi is minus 1. I think I did this backwards in my lecture to my 412 students. When k is equal to 1, we have cosine of k pi. That's cosine of pi. Cosine of pi is minus 1, so it's minus 1 minus 1, which is minus 2. When k is even, cosine of k pi is going to be equal to 1, so 1 minus 1 is equal to 0. Okay, so what this tells us is that when k is even, this is 0, and when k is odd, this is equal to minus 2. So then v of xt I'm going to look at the sum, k equals 1 to infinity. Okay, so bk, I only want to sum over the odd indices. So that's going to be over indices of the form 2k plus 1. So wherever I see a k, I'm going to replace it with 2k plus 1. So what's going to happen over here, if you look at this right here, I'm a little, I'm getting a little tripped up because I know I did this wrong earlier, and I'm just trying to think where I made the mistake earlier. I think I just made an arithmetic mistake, or just whether or not, I don't know, not even an arithmetic mistake. Okay, so now what's going to happen here? I want to only sum over the odd integers. So wherever I see a k, I'm going to replace it with 2k plus 1. Now for the odd integers, this is equal to minus 2, because like if k is equal to 1, it's cosine of k pi, so that's minus 1 minus 1. Which is equal to minus 2. So we're going to have minus 2 over 2k plus 1 times pi, so that's just bk, minus 4. And the reason is if k is odd, this is minus 1, so minus 1 minus 1 is minus 2. You multiply by that 2, you get minus 4. Then you're going to have e to the minus 2k plus 1 pi squared, and then times sine of 2k plus 1 pi x. Now this is v of xt. But if I look at my expression up there, u of xt is just equal to v plus ue. So u of xt is just equal to this plus x plus 1. And now you can see what happens if you, this satisfies this function here satisfies the PDE, because the method of separation of variables guarantees that it satisfies this PDE, but that's the same PDE. If you plug in x is equal to 0, all of these sign terms are 0. That x is equal to 0, then you have 1. So that's just 1. If you plug in x is equal to 1, all of these sign terms are still 0, but now you have 1 plus 1, which is equal to 2. And then if you look at v of x0, well, if you plug in if you plug in t equals 0 here, you get minus 1. Minus 1 plus x plus 1 is equal to x, which is this right here. Okay, so sorry about that. Sorry about the sort of, well, you didn't see the error that I made, but sorry that sort of threw me off. After that, this is an example of using how we can take a non-homogeneous problem and convert it to a homogeneous problem. And we'll do another example after this one.